Hello and welcome to my talk. My name is Sören Hanke and I'm a research assistant at Paderborn University in Germany. I would like to introduce you into one of my research topics with the title Comparison of Artificial Neural Network and Least Squares Prediction Models for Finite-Control-Set Model Predictive Control of a Permanent Magnet Synchronous Motor. Let me start with the introduction and the motivation. The focus of this talk will be on the system models used inside the model predictive control. The considered drive system is shown here on the right side. We have a two-level inverter feeding a permanent magnet synchronous motor. The DQ current of this motor are controlled by a finite control set model predictive control. Model predictive control is able to achieve a high control performance, for example in terms of small settling times and low overshoots. However, model accuracy is key to achieve such a high control performance. The idea is now to extract models of high accuracy from measurement data, so data-driven approaches. And I'm going to compare least squares based and neural network based approaches in this presentation. On the next slides, I will give you a short introduction into the drive system and the principle of the finite control set model predictive control. A dataset details about the modeling approaches and their evaluation will be explained afterwards. Shown on these slides are the ODEs for a drive system consisting of a PMSM in combination with a two-level inverter. We have the motor currents in the DQ reference frame and the DQ voltages, which are defined by the DC link voltage, and the 8 possible switching states or elementary voltage vectors of the two-level inverter. As we have two zero voltage vectors, it is enough to consider only one zero voltage vector in the finite control set model predictive controller. You can rewrite the ODEs into a form where you have an extended system state vector and a system matrix which has the switching states of the inverter as parameters. So you have one system matrix or one white box model per switching state or per elementary voltage vector of the two-level inverter. The problem with white box models is that they only take the fundamental effects into account, neglecting higher order effects like flux harmonics or inverter nonlinearities. With learning gray box or black box models from data, we aim to take higher order effects into account. Before discussing how to extract models that should be used in a predictive controller, let us have a look at the controller itself. The principle of the finite control set model predictive control is to choose an appropriate elementary voltage vector and keep this vector constantly applied to the motor for one controller cycle. To decide which vector might be the best one, you need to predict the behavior with a prediction model for all vectors. To evaluate and to test different modeling approaches, we decided to record measurements into a dataset. The dataset covers the shown IDQ current range at a fixed mechanical speed, DC link voltage and temperature. It consists of about 40 million samples, where each sample is a data pair with measurements at k plus 1 and the information about the vector used between these two time points. When you take into account where a sample or a data pair is located in the operating range of the drive, you can generate or build balanced training datasets where not a region is overrepresented or underrepresented. Furthermore, we made this dataset publicly available so that you can test your own modeling approaches and techniques. The dataset itself can be found on kaggle.com, a platform where you can share those datasets, and it comes together with a comprehensive description in two parts. Part 1 is focusing on the system and the dataset, Part 2 on modeling approaches. The dataset description can be found on arXiv as well as on ResearchGate. You will find the links to both in the paper. Let me now explain the different modeling approaches to you, starting with the online LS. The online LS uses a multiple model structure. That means you have one model per elementary switching vector. The extended system states of the analytical white box model are used as inputs. How to extract such models from measurement data? First of all, you need samples or data pairs consisting of inputs and to be predicted outputs. You collect several of these samples into a batch to build up an overdetermined system. Afterwards, you perform a linear regression on it. With a limited number of regressors, the extraction itself is online capable. That's why we call it an online LS. The next approach is the offline least squares. The idea of the offline least squares is to use more inputs to be able to extract higher order effects from measurement data. To find those inputs, we first build up a regressor set consisting of ID/IQ polynomials up to order 3, sine-cosine harmonics up to order 20, and all possible combinations of these. So we build up a comprehensive regressor set. Afterwards, we use the SINDI algorithm or the SINDI toolbox to find the most significant regressors among these set. The SINDI toolbox uses the iterative algorithm. It performs a linear regression using all regressors in the first iteration and based on a threshold uses only the most significant ones to perform a linear regression on them in the following steps. In this way, we boiled it down to the 24 most significant regressors, which are listed in the vector W as input vector, and the vector W uses the vectors P and Q in that way that you use all the elements of the vector P. Additionally, all the elements of the vector P multiplied by cosine, multiplied by sine, and the same for the vector Q, which gives you in total 24 inputs. Due to the larger number of inputs, it is not possible to extract models from measurement data online capable. That's why the extraction is conducted offline. And that also means that each model has to cover the whole operating range when used online later on. Here we use the balanced dataset to make sure that not a region is over or underrepresented before performing the linear regression. Last but not least, the artificial neural network approach. We used the multi-layer perceptron for each model and trained it according to the supervised learning principle. Furthermore, we added the information about the previously used elementary voltage vector to the inputs, because we found out that this helps the net to better account for effects like the switching transition. Also here we used a balanced dataset for training and validation, and during training we used the backpropagation method in combination with the Levenberg-Marquardt optimization. We had to carry out a hyperparameter optimization first to find appropriate network topologies and test the topologies with 1 to 3 hidden layers, up to 50 neurons per layer, and TANSIG or RAD-bus as activation functions. On this slide, you see the results of the hyperparameter optimization. You see two graphs, each graph showing the mean squared prediction error on the y-axis and the number of A and N parameters on the horizontal axis. The number of A and N parameters are the number of parameters in the topology that are the degrees of freedom to the optimization during training. On the left side, you see the prediction performance of a model that predicts the behavior of a zero voltage vector. And on the right side, you see the performance of a model that predicts an active voltage vector. You can also see that RAD-bus and TANSIG both follow the same characteristics of the curve, and that with a larger number of A and N parameters, the prediction error does not decrease significantly. In this case, I've chosen a trade-off between the prediction error and the A and N parameters of about 170 parameters in the net topology. And net topology that delivers that amount of parameters is a topology with one layer and 21 neurons. Let us come to the evaluation of the different models or the different approaches. For the evaluation, we tested the models at different operating points in the considered ID-IQ current range. These graphs here showing the root mean square of the ID-IQ prediction error. In the top row, you see the different performances for the zero voltage vector, and in the bottom row, the performances for the active voltage vectors. Here in the columns, you see the performance of the artificial neural network on the right, the offline least squares in the middle, and the online least squares on the left. What is special about the online LS? The online LS is, or the extraction of the models with the online LS is online capable. That's why here for every operating point we tested, the models of the online LS are adapted to this specific operation point. For offline LS and artificial neural networks, each model has to cover the whole operating range, as the extraction can only be performed offline. You see for the zero voltage vector that the ANN has a superior performance in comparison to the offline LS and also the online LS. Offline LS and online LS deliver more or less the same performance. The same holds true looking at a performance of the active voltage vector prediction. The artificial neural network delivers the best performance, the lowest prediction error. The offline LS and the online LS are both have a higher prediction error, and the online LS, the prediction error is increasing with an increasing Q current. Shown on this slide, the probability density functions of the prediction error. Each histogram on the right side covers the performance in the whole operating range, but now separated for the ID and IQ current. In this graph, you see the prediction error of the artificial neural network for the current in the Q direction. The distribution of the prediction for a zero voltage vector is nearly bias-free and has a very narrow distribution in comparison to that of the online least squares above. Please note also the different scaling. We have 0.8 for the ANN and 0.4 for the least squares. Also, the probability density function for the prediction of an active voltage vector is shaped towards smaller prediction errors. The same holds true for the prediction error of the d-direction. To summarize, it is possible to extract accurate models from measurement data and data-driven approaches. These models are able to cover higher-order effects like the magnetic saturation. A dataset we have recorded and used for training and evaluation is publicly available, so that you can test your own approaches and modeling techniques. Regarding the compared topologies and approaches, we can say that the Schusen ANN shows a superior performance to both LS approaches in the whole operating range. We see only a small difference between the online LS and the offline LS, especially for the prediction of the behavior at active switching vectors. As an outlook, we might extend the coverage of the dataset to different speeds and different DC link voltages, and we want to analyze the online LS in a recursive implementation in more detail. Thank you for your attention. If you have any questions, please post them on the platform or write me an email.